All right, this video is the third part of the integrated circuit layout design technology. In this session, we will mainly introduce some basic device drawing methods that are often used in layout design. So these devices include MOSFETs, which are our commonly used MOS transistors. Then there are two passive devices, the capacitor and the resistor. First, let's take a look at the layout drawing method for MOSFETs. So in this layout design, we need to define the two most critical levels, which are actually our extremely important polysilicon and active areas indeed. So we use the park to define a rectangular area, and then in this rectangular area we can form an active device. Then we draw another line, draw a rectangle with polysilicon to overlap the active so that the core area of the device is formed. For example, in the picture below, the green thing is mainly the active. Of course, the active must be covered with diffusion, right? It must be covered with doping. In this case, its original leakage area is defined. When we overlap a polysilicon gate, the basic structure of the device is already formed. After that, we need to connect its source and drain to the substrate. We have been emphasizing that a MOSFET is a four-terminal device, so it's crucial to pay attention to its substrate connection. Therefore, we need to connect its source, drain, and gate. It's a four-terminal device, so we really need to pay attention to its substrate connection. Therefore, we need to connect its source, drain, and gate first. Let's proceed with that. After interconnection, you must pay attention to its substrate, or neck. So for our P substrate process, if we want to draw NMOs, then its core must be this P substrate, right? If we want to draw a PMOS, we first need to create an N well. So the substrate for the PMOS is this N well. This means we need to apply a proper bias to the substrate or well, connecting it to the appropriate power supply or ground, right? If it's an NMOS, we need to connect it to the ground, and if it's an N well, we need to connect it to the power supply, VDD. Pay attention to this four-terminal device. For example, if this is an NMOS, then the B terminal must be connected to ground, right? It needs to be grounded. So this is how we draw it. Once we have the basic structure of the MOSFET, we need to ensure that we make a reliable connection. A reliable connection is crucial, as shown in the diagram on the left. In this diagram, if we have a source drain region that is particularly long, for example, if I draw a transistor where the width W is 10 micrometers and the channel length is 1 micrometer, then in this case, the direction we are talking about is the width direction, right? So it has a width of 10 micrometers. If I want to connect the source drain region, specifically the source to the drain, I definitely need to use a contact, right? I will use the contact to connect it to M1. Connect to M1, then I can connect it like this, right? I'll put on a contact near the bottom and then connect it with metal. If I make a connection like this, I'll do this. The DRC check is fine. I say the LVS check will also be fine, because it is indeed connected. But we need to be aware that this kind of connection is very unreliable. Why? Because the source drain region, although the entire area is connected, it is connected through doping, which has relatively high impedance. So, what problem does this lead to? If we use this as a switch and want to pass a current signal through it, for example, if the current flows through this transistor and then out from here, what phenomenon will occur? It will cause this area to have a reliable metal connection which has lower resistance, while the resistance increases as you go deeper in, right? So, in this case, it will concentrate all the current in this area to flow through. The current inside will be relatively weakened. That is, the current inside will be weak. A relatively high current will flow here and this inside. Its current density will decrease, which means low current density here and high current density there. This will significantly affect the characteristics of the transistor. Therefore, we must ensure reliable connections. So how do we make reliable connections? We need to uniformly cover the source drain region with contacts. Evenly cover the contacts. Yeah, evenly cover the contacts. Then we cover the entire source drain region with this metal, M1. In this way, we can say that the potential of the source drain region is basically uniform because the resistance of the metal is very low. It's very low, so it can achieve a relatively low voltage drop. In this case, if we transmit a current with current entering from here and exiting from there, then the direction of the current within this transistor will be uniform. It will be uniform, yes, it will be uniform. So in this case, making a reliable electrical connection is something we need to pay very close attention to. So besides the source drain region, we need to focus on the connections. Another very important thing to note is that when we draw a transistor with a very large aspect ratio, when the aspect ratio is very large, this type of transistor is also commonly used. For example, when we design a low noise preamplifier, its input transistor tends to be quite large, and it could reach this hundreds to one or even thousands to one. Let me give you an example just to exaggerate a bit. Let's say we want to draw a transistor with 1,000 to 1 aspect ratio. If we don't do anything special, if we use special techniques, we can just draw a gate directly and then let its length be 1 micron and the width be 1,000 units. So you can imagine that after this transistor is drawn, it actually looks like a long, thin line, right? It's really long, very long. Now, what problems could this cause? Mainly 2 issues. The first one, for the first one, you can see the original leakage area. The area of the original leakage area is very large. A whole circular path will be very large, which is a problem. If the original path is large, it will bring a problem. That is, the parasitic capacitance of the original path will be relatively large, because we know that there is actually a reverse bias junction between the original drain area and the substrate, right? What about the reverse bias PN junction? What will happen? Indoor capacitance, right? Indoor capacitance. So here, there will be an indoor electrical parasitic PN junction capacitance. If there is a drain area in the park, there is also the capacitance of the biased junction. Its size is related to the area of the original drain, right? The larger the area, the greater the capacitance. The larger your integrated capacitance will be. So if you draw a pencil, then your source drain region will definitely be long and large, which means its body will also be quite big. That's the first point. The second point is that if we look at the gate will be particularly long, right? The gate will be especially long. So we previously talked about how to connect the gate, right? We have to connect it to a contact and then to the metal, right? So I can draw something at this position. I'll draw a contact. For example, at this position, I'll draw a contact here, and then I'll use this metal, M1, for example, to connect the gate out. So in this way, my gate is electrically connected, right? But there's a problem. The parasitic resistance of this gate is relatively large, right? We've also talked about how the gate's integrated resistance is relatively high, reaching up to 200 ohms per square. So if I apply a signal to the gate here, when the entire signal is transmitted into the circuit, there will be an RC issue, right? Although the gate is indeed a capacitive load, right? It won't cause continuous current, but if the gate has a large integrated resistance, then there is an integrated capacitance between the source and the substrate, right? And then the gate also has a large integrated resistance. So what does this mean? It means that our transistor effectively becomes like this. If we want to draw an equivalent circuit model, for example, if I originally connected to D, then the substrate is also connected to D. It's kind of like this. There are many of these on the gate. RC, right? There are a lot of RCs. We previously discussed the distributed model for the RC of metal lines. And this model also applies to the gate, right? So this capacitor is mainly because the parasitics formed between the transistor's source and the substrate. Now this resistance is due to the integrated resistance of the gate's polymaterial, which tends to be quite large, right? If this resistance is large, then if the gate is particularly long, then this RC model will also be particularly long, right? Clearly, this will lead to what? If I apply a signal here, then when it actually reaches the real control terminal, which is the gate terminal, it will definitely cause distortion, right? There will definitely be distortion. If the signal frequency is particularly high, then it's very likely that this signal the signal that truly controls this gate has already disappeared, right? It's gone. So compared to the source drain issues we mentioned earlier, this is even more serious because the source drain issue just means that my parasitics have increased, right? But the parasitics of the gate could potentially lead to the transmission of the signal. The speed can't keep up, and it just disappears, right? It just vanishes. And the parasitics of the source drain, generally, the source drain has to carry current, right? When current flows through, it will always charge the signal up. It's just a matter of time. But the gate is different. The gate is different. So what should we do? Some students might ask, can I just add more contacts in the gate, just like I did with the source? I did that with the source, right? I added contacts there. I also added a row of contacts on the gate, and then covered the entire gate with metal. This way, the voltage actually gets transmitted through the metal, reaching the gate in segments, right? So, the signal that the gate receives becomes very reliable. If we do this, then we can solve this problem in theory, right? But the problem is, usually, the design rule does not allow you to hook it up. Draw the contact. If you hook it to the top, it is more likely to have contact mainly because it is a sensitive structure. If you draw the contact above, it will affect the electrical characteristics of the channel. So, if you draw a contact above the gate, it will usually throw an error when you run DRC, which means you can't do that. Since I can't draw contacts on the channel, I can only place them outside the gate, which means at the two ends, right? I can only draw contacts at the two ends. So, in this case, that doesn't solve the problem we just talked about, right? So when we actually go about laying out the design to tackle the parasitic issues or to address the large-scale transistor, what do we usually use? We can use this finger structure to solve the problem. Now let's take a look at how to create this finger structure. For example, if I take this large, wide transistor and split it into what? Fingers equal to 2, right? Fingers. Finger equals 2. If it is split into finger equals 2, then it means that I cut the 3 into 2 parts, right? Cut it into 2 parts evenly, and then split it into this way of leaking circles. By structuring it this way, let's take another look at the parasitics of the original source. First, let's examine the parasitics of the original source. We find that the length of the drain has become half of what it was, right? The parasitics of the drain have decreased. And for the drain, since there are 2, even though each segment is half of the original, the combined parasitic of the 2 drains remains unchanged. This is with fingers equal to 2, but the parasitic capacitance has decreased. So if you, when applying it, if the body of the transistor is more sensitive, then I can place the fingers drain in the middle position and the source on both sides, right? If the source is more sensitive, then I can have the drain in the middle and the source on both sides, right? That's a choice you can make. Right, this is the parasitic of the original drain. Next, let's look at the gate. The gate has been split into 2 segments, right? So I can place a large contact here. Here, I'll add a contact and then use metal to connect the 2 in parallel, right? Connecting them in parallel with metal. So, in this case, how does the original parasitic change? It gets smaller, right? For example, if the original parasitic resistance of the entire gate is R, then now each segment only has half of R, right? Each segment is only half of R, and then when I connect them in parallel, it becomes even smaller, turning into 2,4, right? It becomes 2,4. So through such an operation, the integrated resistance of the gate becomes much smaller, 4 times smaller. Well, this is equivalent to saying that I use this finger method. Well, the inheritance of the gate is significantly reduced, right? Then let's see if we can have more fingers, right? For example, if my finger is changed to 3, 3, the finger on the right is equal to 3. If the fingers are 3, let's take a look at this situation. Here we have the original source and drain, right? The number of sources and drains is the same, and each segment is now 1/3 of the original. This way, the parasitic of the source and drain becomes 2/3 of what it was, right? The parasitics of the source and drain have changed to 2/3 of the original. Now let's look at the gate. The gate has been divided into 3 segments. In this case, when these 3 segments are connected in parallel, what do we get? It becomes 2,9. So this way, the parasitic resistance of the gate has been significantly reduced. If we increase the number of fingers even more, the impact on the gate is very positive. The more fingers I have, the more effective the gate becomes. With more segments and smaller segments connected in parallel, right, the parasitic resistance will drop significantly. But for the parasitics of the original source, when we increase the number of fingers a lot, the total equivalent area of the source and drain tends to become more consistent with the area that hasn't been split. So it's parasitics. The reduction becomes very minimal. However, the integrated resistance of the gate will drop significantly. So we can use fingers to optimize the parasitic capacitance of the source and drain, as well as the parasitic resistance of the gate in this situation. It is tending to the area that has not been disassembled. So its parasitics and the degree of reduction becomes very weak, but only the integrated resistance of the gate will be greatly reduced. So we can use the finger. Let's optimize the parasitic capacitance of the source and drain of this MOSFET, as well as the parasitic resistance of the gate. So let's take a look at the schematic diagram of this MOSFET layout. We have shown this to you before. This is an inverter, right? It's an inverter. It's the layout of an inverter. Now on the left side we have an NMOS, and on the right side we have a PMOS. Right? Let's take a look. For the NMOS on the left, it must have a park first, right? The black dotted box is the park. And outside the park, there will be an N-positive injection. And usually the N-positive injection is larger than the kindergarten area. So what is the term used to describe this? It is enclosure, right? That is, the N license must be active in the enclosure. And the distance of the enclosure, that is, if my N license exceeds the distance of the park, there are certain requirements. There will be specific constraints in this design rule. So let's use the gate poly to cover the entire right well region. This way, we form the channel region. Then, on both sides, we draw contacts and connect them with metal. Now, for an inverter, the output terminal needs to be grounded, right? At the same time, my NMOS also needs to have a substrate contact. N+ doping requires a well region. It needs an active area. This forms the NMOS substrate contact. Body and source terminals need grounding. Connect them to the ground line. PMOS needs an N well. Draw the N well. Create an active area inside and cover it with PMOS. The end of the body is also grounded, and the original end is also grounded. So connect the body contact and the original end together, and then connect to the ground wire. On VSS, for this PMOS, it must be processed in the N well, right? So first I have to draw this N well, this sky blue N well. So inside the N well, I need to create the PMOS. First, I need to establish an active area and then cover it with the PMOS. So with the P+ doping, we create the PMOS. The N well also needs to be biased, right? The bias for the N well is N+. So there will also be an active area along with the N+ doping. Now for the PMOS, its source terminal needs to be in contact with the well. They are all connected together and grounded. So then we connect the two gates together, and this is the input. Then the two drain connection points are the output, right? This is a typical layout of an inverter. Now, the schematic looks like this, right? This is its schematic diagram. This is the input, right? This is V in. And what is this? This is V out. And below it is VDD and VSS. This is the schematic diagram of an inverter and its layout. Next, I want to introduce a concept called TGO, which stands for triple gate oxide. Earlier, we briefly mentioned it. Now, let's dive into what this process actually does. So this technology is mainly designed to provide two types of transistors with different thresholds. Generally speaking, a process will offer two prefabricated transistors, one with a high threshold and one with a low threshold. The main reason is that for low threshold devices, the channel length needs to be very thin, which allows them to operate at lower voltages, right? So, for low threshold devices, their dimensions can also be quite small, and their operating voltage can be low. The main benefit of this is that it can save power. Secondly, it can reduce the area. So, for digital circuits, they will often use these low threshold devices. But it's different for analog circuits. For analog circuits, they prefer devices with better intrinsic characteristics, right? So, in that case, the channel length generally needs to be longer, which means the size has to be larger. Additionally, to allow the signal amplitude to be wider, which means it can withstand greater noise, right? The channel ratio will be better. So they prefer to use higher voltages, right? Of course, the trade-off that comes with this is that power consumption and area will have to be sacrificed, right? But this is necessary. Only by investing the corresponding power consumption and area can the performance of your circuit meet your requirements. So in this case, there will be relatively high performance transistors and larger size transistors, which means there will be high threshold transistors. For example, let's take a typical example like the 180 nanometer process. So generally speaking, it can provide two types of devices. One is a 3.3 volt device, and its channel length is typically around 0.33 micrometers. Or it could be 0.35 micrometers, something like that. The structural length, this is the detail of the high voltage mold, and there is also a low voltage one, for example, 1.8 volts. Then for 1.8 volts, its hook can reach 0.18 microns. So this device can be used to make digital circuits, right? It can be used to make digital circuits or analog circuits that do not require very high precision. What about 3.3 volts? It can be used for those high-demand analog circuits and also for I/O interface circuits. Finally, when the entire chip outputs to the outside, the voltage will be relatively higher, which means using the 3.3 volt device for the I/O. So in this case, we need two types of devices, right? Two kinds of devices, which means we need two different silicon oxide thicknesses. The silicon oxide thickness for the 3.3 volts needs to be thicker, while for the 1.8 volts, it needs to be thinner. So in that case, we need to use a new photolithography board, which is the TGO layer. How do we do it? First of all, if we do three things, the first thing is to generate one for the whole chip and grow it to a certain thickness. For example, let's say we grow a 10 nanometer one. For example, let's say we grow a 10 nanometer thick one. Then what? After adding the TGO layer, what do? We need to etch away everything outside of the TGO. The part that was initially grown outside of the TGO is removed, leaving only the 10 nanometer thick gate oxide beneath the TGO. We have the 10 nanometers in place. And then what do we do next? We grow a layer across the entire Vivo. Oxide growth, then we grow another layer of oxide. The thickness of this second oxide layer is relatively thin. For example, let's say I grew another one. This, for example, let's say 5 nanometers, just randomly using 5 nanometers. In this case, it's only 5 nanometers, right? On the left side, because it originally had a 10 nanometer layer. First, where is it, right? Now I've added 5 nanometers, so this becomes 15 nanometers. Right? So you see, with this operation, the thickness of the left side gate oxide is thicker, while the thickness of the right side gate oxide is thinner. This means that the left side device has a higher threshold voltage, so it operates at a higher voltage, right? So this means that the VTH on the right side of the gate with a higher voltage is thin, so the turn-on voltage must be low, which is the VTH leakage. In this case, if the gate is processed again, then the thickness of the oxide under the gate on the left side must be, the left side is thicker and the right side is thinner. In this case, the left side is a high voltage device and the right side is a low voltage device. Since the entire process has gone through 1233 steps, it is called triple gate oxide, which is a layer of TGO, its function. Alright, let's take a look at a typical MOSFET and see what its layout looks like. Specifically what it looks like. Let's check it out. So the one on the left is its complete map. The shape, it grows like this. All the layers are stacked together, and then the outer direction is its WX direction, and its L is its length. Then this is its source end. This is the drain end. This is the gate. This is the substrate. And this is the substrate. Of course, for this device, its source and drain are symmetrical, right? You can use the left side as a circle or as a drain. It depends on how you connect the components in the end. Well, let's break this thing down. Breaking it down means taking apart all the levels and seeing what levels it has. Let's take a look at what the core is. As I just said, the core is the active plus the gate, the active plus the gate, the active plus the gate. When the two rectangles overlap, this is defined. What is it? It's the gate definition, right? So in this entire area, we cover it with N+, which is the N-type doping. This way, I've defined the source terminal, right? I've done the injection. Now, how do I connect the source terminal out? I need to make a reliable electrical connection. So I use this white contact to uniformly cover the source drain region as a contact. And then we use this M1 to make a connection. So the source drain is connected out. At the same time, there's another layer. What's it called? It's TGO, as we just discussed, right? Triple gate oxide. So what does having TGO mean? It means it's a MOSFET formed after oxidation, specifically a high voltage device, right? So with that, our source drain region is all set up. Now let's take a look at the gate. The gate also needs to be connected out using contacts and metal, and this is how the gate looks. That's fine. And don't forget about the substrate bias, right? Since it's an NMOS, its substrate is P-type. So first, we need to have a well region, and then we cover that well region with P+. Also, make sure to use contacts and metal to connect it out. So, with this metal, we basically connect it to VSS, right? With VSS, the NMOS is now essentially drawn up. Now, in different processes, the names of these devices can vary. For example, in this typical case, this device is called NCH3, which means it's an N-channel device, and the 3 indicates that it's a 3.3 volt device. So N-3, that's an NMOS. Let's take another look at this PMOS. So, on the left side, this is also the layout of a PMOS, specifically for the PCH3 P-type channel MOSFET. The 3 indicates that it's a high voltage device, right? After breaking it down, we can see what layers are inside, right? First of all, what's the most critical part? It's the active area and the gate, right? The core region is the same, the active area plus the gate. And then we use this contact to uniformly connect the source terminal out with M1, and the gate is the same. What should we cover with it? Cover it with NPL, this P+, right? Because it is a PMOS P+. And then cover it with TGO, because it is a 3.3 volt period. If you are a 1.8 volt device, for example, if it is this PCH does not add this 3, which means 1.8 volt period, then you do not need to add this TGO layer. Then note that this is a PCH, right? The flagship of the P channel, so we must draw an N-while, right? NY is the entire device. All areas must be in this N-while, right? On the left, you can see that N-while is a white box, and all the structures are in this NVL. And don't forget about the substrate. At this point, for this P-type device, its substrate is our N-well, right? This is its substrate, and this is also its substrate. So it's crucial not to forget this. Therefore, the substrate must be connected with N+, right? Then connect it to NY. We say N++ the well region, and then the corresponding contacts and metal. Then we connect it to VDD, and that way we've set up the bias for this device. So this is the layout for a P-channel MOSFET. Okay, so the above is our MOSFET, which is also the most widely used active device in centralized circuits, MOSFET. Next, let's introduce two of the most commonly used passive components, capacitors and resistors, right? First, let's take a look at capacitors. The structure of a capacitor is actually quite simple, right? For a parallel plate capacitor, its most basic structure consists of two parallel metal plates with an insulating dielectric layer in between. These two plates serve as the capacitor's two electrodes. This is what makes up a capacitor, right? So you can see this is how it works. Two electrodes. This is a capacitor device, right? So you can see that this is what it means. When we don't consider edge effects, we have an upper plate and a lower plate, right? Two metal plates with some kind of insulating dielectric in between. This setup forms a capacitor. How big is the capacitance? The size is given by the formula. C equals. The vacuum reference constant is multiplied by the relative reference constant of the medium, and then multiplied by the width and length of the plate. This means that this is the area of the plate, right? Then divide it by the thickness of the dielectric layer. This is the size of the capacitor. So you can see if we want to change the size of the capacitor, how do we change it? There are only three aspects, right? Either we change the dielectric material of the dielectric layer. Well, either change the thickness of the dielectric layer or change the area of the metal plate, right? All three aspects can be changed. Then let's look at different materials. They all have different relative dielectric constants, right? Relative dielectric constant. Then in our integrated circuit process, the common insulating medium is silicon dioxide, all silicon dioxide or silicon nitride. So its dielectric constant is fixed, right? After you choose the process, its identification constant. You can't change the relative node constant. So for the designer, what can be changed? There are actually two aspects that can be changed. One is the thickness. The thickness of the oxidized insulating layer is also related to the area of the metal plate, right? The area of the metal plate. Then let's take a look at the thickness. You can't change the thickness flexibly. Of course, you can choose. Generally speaking, a process will provide different thicknesses so you can modify it. But once it is set, it basically won't change. So what can be changed? The area of the metal plate is the most flexible for design. For example, I draw a capacitor of 5 microns by 5 microns. Right, so this is a type of financing. If I design a capacitor that is 10 micrometers by 10 micrometers, then of course your circuit will be different from that one, right? So we can change the size of the capacitor in this way. Now let's take a look at what types of capacitors are offered in integrated circuit processes. And how is it drawn? First of all, in integrated circuits. In integrated circuits, there are mainly two types of capacitors. The first type is called poly to poly, and the second type is metal to metal. Let's take a look at this. It's quite easy to understand, right? The first type is, what does it mean? It refers to a capacitor formed between two polysilicon layers. So the upper and lower plates of the capacitor are both polysilicon, and in between, there's an insulating dielectric. This setup constitutes a capacitor. This is poly to poly, and metal to metal is also easy to understand, right? It is an insulating medium between two metal clips, and then it forms a capacitor. So let's take a look at poly to poly and poly to poly. What does it mean? You must have two layers of poly, right? It has to have two layers of poly to work. It can be made into this kind of device, but if you only have one layer of poly, then it won't work, right? For example, we previously mentioned I have an EP4M process. Can this process provide capacitance? Clearly it can't, right? It only has one poly layer. But if you have a 2P4M process, then... so this process might provide poly to poly capacitors, right? It has two layers of polysilicon, so if we draw a cross-section, it looks like this. If you only have one layer of polysilicon, then you only have this one, right? You can't form a poly to poly capacitor. You need two layers of polysilicon, like poly 1 on top and poly 2 below. Between poly 1 and poly 2, there's an insulating dielectric, so this forms a polycapacitor, right? A polycapacitor. But this type of capacitor is generally used in processes with relatively larger feature sizes, typically in processes above 0.35 micrometers. Usually, you'll find polycapacitors in processes that are 0.35 micrometers and above, and below 0.25 micrometers. Currently, we mainly have metal-to-metal capacitors. So, compared to that, what issues does poly to poly have? One problem is that the processing layers of the polysilicon determine its characteristics. Poly 1 is definitely very close to the substrate, right? So in this case, the parasitic effects on the substrate are quite significant, making it difficult to avoid interference. It's influenced by the substrate, so you can see you can create an N-well isolation underneath, and we'll discuss in detail later how to achieve that. This is a method of isolation. Of course, this means that due to its inherent defects, you have to consider isolation when you're designing, so this makes the design quite complex. There are quite a few limitations. So, this is a problem with poly to poly. Currently, advanced processes are using MIM or MOM. So what are MIM and MOM? Let's take a look. The metal-to-metal capacitors are also divided into two types. One type is the MIM capacitor. MIM stands for metal insulator metal, which means it has a metal layer, an insulating layer, and another metal layer. So, what kind of structure is this? It's a sandwich structure. If we draw a cross-section, it looks like a sandwich structure. Now let's take a closer look at how it's drawn on the layout. First of all, it definitely has two layers of metal, right? It's metal to metal, so there are two layers of metal. Because of the structure of the parallel plate capacitor, how are the two layers of metal made? First of all, we need a M-top. There's a top metal layer, right? The top metal. Then there's also the top minus 1 metal, but this isn't absolute. It could be that the top metal is M-top minus 1, and below that you have M-top minus 2, right? For example, if I have a 4M process, then my top layer is M4. So I have M4 as the upper plate, and below it is M3. Right. M3 and M4 form the two plates of the capacitor. And as we mentioned before, there must be an insulating dielectric between M3 and M4, right? There is definitely an insulating dielectric in between. So in this way, a capacitor structure has already been formed, right? I'm using M3 and M4 as the metal plates, and in between there's an insulating dielectric. There must be capacitance between these two layers, which creates a capacitor structure, right? This is a shell, and it indeed has capacitance, but the problem is that the capacitance density is relatively low. What do we mean by capacitance density? It's the capacitance value per unit area, right? So I have this. It can form about how much capacitance per square micrometer. If it's purely relying on the parasitics between M3 and M4, then the magnitude might be around 0.1 femtofarads per square micrometer. So if you draw a metal plate of 1 square micrometer, it contributes 0.1 femtofarads of capacitance, and that density is very low, really low. So for example, if I want to create a capacitor with a capacitance of 1 picofarad, what should I do? I need to draw a capacitor of 1 picofarad, which is 1000 femtofarads, right? 1000 femtofarads. If you divide that by 0.1, then you need 10,000 square micrometers, right? You need 10,000 square micrometers. 10,000, huh? That's the area I need to achieve a capacitance of 1 microfarad. But what does an area of 10,000 square micrometers actually mean? Let's calculate it. It's roughly 100 times 100, right? 100 times 100. So it's 100 times 100 square micrometers, right? 100 micrometers by 100 micrometers. I need to create such a large area just to make a 1 microfarad capacitor, which is a huge waste of space. Really a huge waste of space. So what can we do about it in terms of manufacturing? We just talked about capacitors, right? So what are the key factors that affect capacitance? There are just a few parameters, right? First of all, I can't change the ring because the material is fixed, right? Now, since I want to create a larger capacitance, I definitely need to increase the area, but I don't want to make it too large, right? So what can I do? I need to reduce this thing, right? Reduce the thickness of the insulation. Once the thickness of the capacitor is reduced, the density of the capacitor will increase, right? So how can we reduce the density? How can we reduce the distance, right? The distance between the third and fourth is fixed, and the processing process is fixed. So what can we do? In terms of technology, we can provide something called MCT. MCD. So this layer of metal can actually be understood as what we call M3.5. It means that, in reality, this layer doesn't actually exist, but conceptually, you can think of it as M3.5. It's also a metal, and it lies between M3 and M4. So what is its function? It is the real superior version of this capacitor. Then, what is the connection between this superior version and M4? It is through the pupil, so the blue one is actually a through hole, versus via 3. That is to say, the existence of this layer of metal blocks the connection between via 3 and M3. So after adding MCT and via 3, M4 is actually connected to MCT through via 3, right? In this way, MCT forms the superior version of the capacitor, while M3 is the lower version, and there is an insulating medium between MCT and M3. The position of MCT is adjustable. If I place MCT very close to M3, it means that the thickness of this area, TOX, can be made very thin. Once the packaging is done, what does that mean? It means that my density has increased, right? And there's an advantage. The distance of MCT from M3 can be adjusted. It's adjustable within the entire range from M3 to M4. It can be high or low. This means that a single manufacturing process can provide different capacitance densities for these capacitors. But you need to be aware that during the manufacturing process, since it's a full chip, it can only use the same MCT, right? So once you set the distance for this particular wafer run, that's it. The distance across the entire chip is set to this specific distance. Although it can provide different distances, in a single manufacturing run, you can only have one distance. You can't say, oh, for this wafer run, I want to provide 2 different distances. That's just not possible. So this distance means there are different unit capacitance values, right? If I make that distance a bit closer, then for example, I could provide 1 microfarad per square micrometer, right? So if I bring it in a bit more, then I could provide 2 microfarads per square micrometer, right? but you need to pay attention to the difference between 1 microfarad and 2 microfarads. This process can provide options, but it can only offer one at a time. You can't choose both. You have to pick one. So this is the role of MCT. With this structure in place, let's take a look at its 3D diagram. It looks like this. There's a top-level version, the MCT, relying on Wi. M4 connects above M3. The process choice varies. MCTV3 and M4 combine and connect, forming the capacitor versions. In the middle is the dielectric layer, thickness, Tox. 3 connected to this M4, and then there is an M3 underneath. This is the example I gave of using 3 and 4. It could also be 2 and 3, right? This is different. The process is different. So this means that MCTV3 and M4 are combined together. What about them? In fact, they are connected together, right? So they jointly form the upper version of the capacitor. And this is the lower version. So here is its upper version. And this is also its lower version. In the middle, this is its dielectric layer. And its thickness is Tox. As for Tox, it can be adjusted. It can be adjusted. So this is a sandwich structure, right? It has 3 layers, so it is called a sandwich structure. Then there is another structure called MOM. Actually, it is just a question of naming. The O in MOM stands for oxide, right? Actually, oxide is also an insulator, right? It is just called metal oxide metal in the name. What is the structure of this MOM capacitor? It is a flux structure, that is, a paper-inserted structure. Generally speaking, for more advanced processes, it will provide such a capacitor. So what is its actual structure? It is actually the same layer of metal. We create this kind of insert paper structure and then interleave them together. After interleaving, it forms this kind of capacitor. Let's take a look. For example, this is our metal, a certain layer of metal. Let's say it's M, for instance, M4. So for this M4, let me first draw a comb-like structure, right? Then I'll draw another comb-like structure, and I'll connect these two together. Yes, plug it in. What about this? One is the left plate of the capacitor, and the other is the right plate of the capacitor. So how is the capacitance formed between them? It's based on what? It's based on the gap in the middle, right? The dielectric layer, right? What is this? It's the oxide, and it's formed by this material. Now, where is the metal plate? The metal plate is on the side of this wire, on the sidewall, right? We've talked about how this sidewall has a certain thickness. So once you draw this insert paper structure, the area of the expanded sidewall is relatively large. Therefore, when you consider its equivalent, the area of the capacitor plates is quite large. This is how the capacitor structure is formed, through this method. Let's take a look at its 3-dimensional structure. This is what it looks like. On the left side, there's an insert paper structure. And on the right side, there's another insert paper structure. However, both have a certain thickness. This means that the sidewalls between these two insert papers, right? These sidewalls here and there, etc., all have integrated capacitors present. So these capacitors make up the capacitor device, right? So you see this capacitor, right? So what affects the unit capacitance? Is it the distance between the two interpolation values? If the distance is very close, the density will increase. Otherwise, the density will be low. So by adjusting the density, then by adjusting the size of the capacitor, what can be controlled? The number of insert papers and their length, right? Both can be used to control the size of the capacitance. Note that this is the structure of the MOM capacitor. So let's take a look at what parameters might affect the accuracy of the capacitor. The factors that affect the accuracy of capacitance. In other words, the capacitors produced by integrated circuit processes are actually not precise. They have errors, and these errors can be quite significant. Their absolute error is relatively large. For example, if I want to create a capacitor with a precise capacitance value in my circuit, like a specific value, that's unrealistic. It's very difficult to manufacture a capacitor with an exact capacitance value. So, the parameters that affect the accuracy of the capacitance mainly include several parameters defined within the circuit, right? Let's take a look at what these parameters are. First of all, there's the relative permittivity. If your relative constant changes, your capacitance will definitely change. So, what things will affect the relative dielectric constant? There must be a few things, right? The loss and damage that evolve will definitely affect it. And if some impurities exist in the oxidation process, they will also affect the node constant. And then, what else? The electrical bias state of the capacitor. That will also have an effect. Additionally, during the oxidation process, we use chemical vapor deposition, CVD, right? In CVD, we also apply this bias. The electrical bias. This bias will also affect the dielectric constant, right? And then there's stress and temperature, right? All these factors can influence the dielectric constant, specifically the relative permittivity, which is part of the dielectric constant. Now, the second part is the thickness of the oxide layer. When it comes to the thickness of the oxide layer, the first thing that comes to mind is its growth rate, right? If the growth is fast or slow, then the thickness will definitely be different, right? Also, the size of the area being processed can affect the thickness as well. Finally, there's the issue of the width and length of the metal plates, right? The changes in these dimensions mainly come from etching and alignment errors, which can lead to the width and length of the processed capacitor not being what we intended. So, in the end, it results in our capacitance not being accurate enough. This means that it's really hard to guarantee absolute accuracy. But fortunately, in our circuits, the integrated circuit processes can maintain a relatively good level of what? Relative accuracy. The so-called relative accuracy means, what can I do? Two identical capacitors. Hey, I want these two capacitors to be this. The degree to which the capacitance values are close can be relatively well guaranteed. However, of course, if you want the capacitance values of the two capacitors to be more consistent, some sacrifices are also needed, like their area might need to be larger. We'll talk about matching later, and we'll cover this topic then. When it comes to matching, we'll talk about how to make these two components as consistent as possible. So, while absolute accuracy is hard to achieve, relative accuracy can be done quite well. In other words, it's very difficult to create a batch of capacitors that are all precisely the same, but I can definitely make two capacitors with similar values, and that's achievable. It is precisely because it has this relative matching degree that this capacitor can be used for some signal processing, such as the switching capacitor we commonly use. Switched capacitor circuits. Well, it is the most commonly used circuit structure in the current mixed signal circuit. It uses switches, capacitors, and amplifiers to form some circuit structures to realize analog signal amplification, integration, addition and subtraction operations, etc., right? In this process, it's about using capacitors for charge transfer and signal operations. We'll use the ratio of capacitors like C1 over C2 for precise calculations. This concerns capacitor accuracy. Now let's examine a typical MIM capacitor structure. It has a sandwich structure starting with a top metal layer, M4, in an EP4M process. Below M4 is V3, MV3, or VA3. If there's a proportional relationship I can calculate precisely. This concerns capacitor accuracy. Let's examine a MIM capacitor structure. It has a sandwich structure starting with top metal M4, an EP4M process. Below M4 is V3, MV3, VA3, and then MCT. These layers form the upper layer. As mentioned before, it is a sandwich structure, right? So it must have a top metal first, M4 for this. This is an EP4M process. EP4M process, first there is M4, then what is under M4? V is also 3MV3, this is VA3. And then below that is MCT. So these three layers together actually form the real upper layer, right? This is the upper layer. They are connected. What's the lower layer? It's M3. These layers form the capacitor, the MIM capacitor. Summer edition. This is its lower layer. So, when these layers come together, they actually form the capacitor, right? We have these layers, a total of 4 layers, and they already make up the MIM capacitor, right? The MIM capacitor. And then, let's take a look at what's on the right. It's called EMCT, and there's this thing. What is this thing? We can understand it as an auxiliary layer. The auxiliary layer, that is to say, it does not have a real studio version corresponding to it. For example, these 4 layers have real masks corresponding to them. That is to say, these 4 layers will participate in the real lithography process. But this, the MC is different. It is an auxiliary layer. Its main function is to make this to make the DRC tool and LVS tool recognize that this thing is a capacitor. And it won't be understood as just simple wiring, right? Because M3, MV3, and M4 are all wiring, along with vias and such. If we don't add the auxiliary layer, the software would have a hard time distinguishing whether it's just metal wiring or an actual component, right? So by adding MCT, we indicate, oh, this is a capacitor. It's mainly for auxiliary purposes. Of course, you have to draw it. If you don't, you won't be able to perform verification later on. You won't be able to do it. So this is the capacitor. Well, finally, let's take a look at the resistor. As for the types of resistors, in the automatic circuit process, there are relatively many types of resistors, unlike the capacitor just now. Although there are PIP, MEM, and MOM, but for the same process, it generally only provides one type of capacitor. It will not provide this one at the same time. You can't get both PIP-compatible capacitors, MIM capacitors, and MOM capacitors all at once. That's not possible. Generally, they only provide one type. For example, for a specific feature size, like above 0.5 or below 0.25, they might only give you a MIM capacitor. Or in dense circuits, there's usually only one type. So when it comes to capacitors, you generally don't have options. There's only one type available. But resistors are different. For the same process, resistors can offer you several types to choose from, quite a few options. Now let's take a look at the different types of resistors and what distinguishes them. First, let's consider the resistors formed by N-type doping. This resistor is actually created by drawing a block of N-type material on a P-type substrate, and then inject the N-positive into the two ends and connect them with the contact and metal. This will form a resistor for the N-positive input and output. So what about the square resistance? Generally, it is about 200 ohms. This is the N-positive main line. In addition to the N-positive injection, what else can be done? P-certificate injection. If I want to inject P-certificate, I must draw an N9 first, right? Draw N9 first, then draw the P-positive injection in the N-well, and then connect the two ends of the P-certificate with this contact. We also need to pay attention to properly biasing the N-well to VDE for the N-type connection, right? So, the square resistance formed by P-type doping is also around 200 ohms. In other words, whether it's N-type or P-type doping, the resistors formed through this method generally have a square resistance of about 200 ohms. This is N-type and P-type doping. Now we can also look at what else? N-wells. We can use N-wells to form resistors as well. So I can draw an N-well and then inject N-type material on both sides to connect it out. This way we form an N-well. The square resistance of the N-well can be quite large, reaching up to 1000 ohms per square. And then what else can we do? We can also have this pinch effect, which is a forward biased N-well having a forward biased N-well. So what does forward biased mean? It means that I add a P-type doping on the surface of this N-well. And then I add a P-type injection. And then this... I can also connect this P-type to what? I can connect it to the D line, right? So I connect this P-type to the D line, and then the bottom part, this pizza, is also connected to the D line. Then I connect both ends of the N-well using N-type material. This way we form a forward biased N-well. Now, what's the purpose of doing this? Why do I want to create a forward layer of N-type material on the surface of this N-well? The main issue is that, let's take a look at the scene above. The surface of this N-well is actually the surface of the wafer, right? And on top of that, there's silicon dioxide. So, in this way, the surface of the N-well has a broken lattice, right? When it comes to exercise, what will happen? There will be a lot of what we call, what's it called? Hangings. Yeah, hangings. So these hanging parts are defects, right? The defects in the lattice will become the loser or the receiver, and in this case, it will affect the characteristics of the noise. It will affect the electrical noise characteristics. Because these suspension parts will randomly release or capture electricity, then the current on the resistor will definitely fluctuate, so it will increase the noise of the resistor. So how to reduce the noise? Well, I can inject a batch of sound on the surface, and then what? Where is this defect? The defect is at the interface, right? It's at the boundary between the bulk and the oxide, and that's where the interface is. So in this case, the bulk has these hanging defects. But I've connected the bulk to the D line, right? The potential of the bulk has been pulled down. And between the N-well and the P bulk, the lattice is perfect, because it's based on injection, and there are no defects in that lattice. Alas. So, in this case, there will be no hanging wires on the surface. In this case, there will be no noise caused by hanging parts or surface defects. Therefore, the noise characteristics of such resistors will be better. This is the resistor with avant-garde. The N-well resistor of avant-garde, of course, its square resistance does not change much and is also at the order of thousands of ohms. Now let's take a look at the next type. What is the next type? It's the polysilicon resistor formed by polysilicon. Its structure actually consists of a polysilicon layer, and then the contacts and metal are connected on both sides, forming this polysilicon resistor. To shield the noise from the substrate below, a guard well can also be added under the polysilicon. This way, it isolates the noise from the substrate. Of course, we will discuss this in more detail in the noise section later. This is the polysilicon resistor, and there are actually several types of polysilicon resistors. They can be either injected or non-injected. What else can you add to the poly? Add injection, because it is pure poly. Its capacitance is too high. A p-type or n-type injection is added, creating n and p wells. There's also the silicide process, which reduces resistance. To enhance resistance, remove elements. Polysilicon resistors range from 10 to several hundred ohms, depending on injection. This process is called the silicide process, which involves metal silicide. With this process, the resistance can be further reduced. To enhance the square resistance, certain elements can also be removed. Generally, the range of polysilicon resistors is quite broad. It can be from 10 to several hundred ohms, depending on whether there is injection. Is there injection or not? Is there this? In different situations, the organization of this cube computer will change. Let's take a look at what this is. First of all, during the integrated circuit processing, the entire area is actually coated with this material, and then the positions that need electrical connections are left intact, while the rest is etched away. The active area, region above, and gate are covered with a purple layer. This layer reduces resistance. Connections to source and drain improve, thus parasitic resistance lowers. We want to use the gate as a drain. When used as a drain, its square resistance should be larger as too small. So this is a material with relatively low resistivity. The purpose of covering it is to reduce what? To reduce resistance, right? I can make the connections to the source and drain better. So, with this, we can lower parasitic resistance. So right now, we actually want to use Git as a resistor. When we want to use it as a resistor, I actually hope that its square resistance is a bit larger, right? A bit larger, because if it's too small. To achieve resistance, a larger area is needed. If the gate's resistance is 1 ohm, 1000 ohms needs 1000 to 1 gate. If it's 100 ohms, a 10 to 1 ratio suffices. In resistor devices, higher gate resistance is preferred, avoiding metal silicide on the gate. The contact layer is covered during processing. A gate with 1000 to 1 ratio is necessary, right? That would sacrifice too much area. But if my square resistance is 100 ohms, then a 10 to 1 ratio would be enough, right? So when I'm making resistor devices, I actually hope that the resistance of the gate is relatively higher, so I don't want there to be any metal silicide on the gate. But the problem is that for processing, the entire contact layer is covered. So this is without any special considerations, right? Everything has been added. Now I need to do a special treatment for the gate. So what do? There's a special layer called SAB. So what is it? Sally said a block. It's the metal silicide barrier, right? So after I draw this thing, the thing underneath is no longer there. When processing, if there's SAB, it won't be processed. Only if there's none will it be processed. That way, when I draw the resistor, what can I put on the git? SAB, right? After drawing the SB, the thing underneath is gone. The resistance of this block will naturally increase. So let's take a look at the layout of this resistor. Let's take such a device as an example. The one on the left is the complete device, the structure of the layout, and its name is U3. Let's explain the origins of these names. First of all, R. It starts with an R. What does it mean? It is a resistor device. R starts with resistor. And then there is N poly, right? N polo, we just talked about this poly. It usually has an injection. Otherwise, the integrated circuit would be too large. So, N poly means that there needs to be an N-type injection across the entire poly, right? And then there's a U at the end. U means unsatisfied. The mountains of Anshan. That is, it is not added. What does the owner of this gold have to draw on it. SAB is the 33 block, right? And there is a 3 at the end. Note that this 3 is different from the NCH3 we met before. The 3 in NCH3 represents voltage, right? Is it 3.3 volts or 1.8 volts? But this 3 represents a 3-terminal device. So someone might ask, isn't this device just a 2-terminal flagship, right? This resistor is a 2-terminal device, A and B. So how can there be a 3rd terminal? Well, note that for this device there is a 3rd terminal. What does the 3rd terminal connect to? It connects to the ground. This thing? This thing means that the area around this device needs to have a grounding treatment. What's the purpose of this grounding treatment? The goal is to improve the electrical characteristics of the substrate beneath the resistor, because this resistor is on the gate, right? The gate is processed on top of the substrate. The purpose is to enhance the electrical properties of the substrate under this resistor. Because you are grounded, the substrate underneath will not have voltage fluctuations. So in this case, the noise of the resistor will be low, right? So what is its actual purpose? It is to low noise. To make the substrate's electrical fluctuations smaller, right? After we open it up, we can see that it has several layers. First of all, the core is the gate, right? We need poly because it's a resistor, a poly resistor, right? So it has poly. And since it's N-type, there needs to be N+ as well. So, in order to increase the square resistance of this device, I need to add this block, right? It's still AB. After putting this thing together, I also need to add the original source region, right? The 2 ends of the resistor, right? One end of the resistor is here, and the other end is over there. I need to make this electrical connection go out. So here, we need to pay attention to the 2 ends of this resistor. They definitely need to be covered with N+, right? Because when these 2 connection points are connected, I want their resistance to be low, right? So this 33 block must not cover the connection area. You can see that the red color stops right here, right? There isn't anything on top of this connection area. Blocked means there's no side block. So when these layers come together, they actually form the resistor device. Right. Now let's look at the 2 other things behind, which are Rn dummy and dummy Rm. What are these 2 things for? Well, just like the capacitor we talked about earlier, they are also auxiliary layers. Of course, it's important to note that these auxiliary layers more, right? It has 2 auxiliary levels. This is it. This is a drawing method for resistor devices. All right, that's all for this video.